Okay.
All right, so good afternoon. Welcome to the CERIAS weekly security seminar. My name is Dongyan Chu. I'm a professor in the computer science department and CERIAS. I'm the coordinator of the seminar series for this semester. And today it's my pleasure to introduce Zhenjun Huang. He is a PhD student in the computer science department at Purdue. His advisor is Professor Xiangyu Zhang. Zhenjun is interested at programming language, program analysis technique and their applications to detecting malicious behavior and vulnerabilities in mobile apps. And his research combines static program analysis, text, and GUI analysis. So without further ado.
Thanks for the introduction. Good afternoon, everyone. My name is Zhenjun Huang. And today I want to share with you our work on detecting sensitive user inputs for mobile apps. This is a joint work with Zicun, Xu Shen, Zheng Yu, Guofei in NEC Labs, and Kang Jie from Georgia Tech. And this work was started when I was an intern in NEC Labs and was published in Usenix Security 2015. In this talk, I may frequently talk about something like text labels, input fields, and input hints, UI widgets, or net files. So before we go into the details, I want to quickly introduce some terminologies. The user inputs, fields, and the text labels and the input hints are what the users see when they use the mobile apps. And in this example, we can find that this text label, the input field, and the hint of the input fields. And the text label and the input fields are called UI widgets. And the layout files are provided by the developers to statically define the UIs. And these files can contain the definitions of the UI widgets as well as certain attributes. As in this example, the identifier of the widget is defined here, and the developers can reference this widget via this identifier in the code. And some interesting attributes here can indicate the expected types of the inputs. Okay, then I want to start our main talk. Recently, smartphones and mobile apps have been an essential part of our lives. At the meantime, users' privacy has become a major concern. And in mobile apps, it's very common for the apps to disclose the sensitive user data to local storages, to logs, or to some external public channels like internet. But unfortunately, such disclosures may be hijacked or maliciously retrieved by adversaries, leading to some serious leakage of users' privacy. And a lot of research efforts have been spent on this area, but their focus is largely on the sensitive data that are defined by certain APIs. For example, the APIs that can return the phone's identifier or return the phone's current location. And most of these data are permission protected. Together with some approaches that are also published in Usenix Security 2015, our work is among the first to detect user inputs as sensitive sources in mobile apps. And it's very common for mobile apps to have user inputs, and none of them are permission protected. Therefore, we need to understand the context of the inputs to determine whether these inputs are sensitive or insensitive. One example is that the input of a credit card number is sensitive, but the comment for an app is insensitive. And for the sensitive user inputs, the data flow is something like this. The data is retrieved in the code and later disclosed to some public channels like internet. But for the insensitive user inputs, the data flow is the same as that of sensitive user inputs. Then if we want to do some disclosure analysis, we cannot simply find out the sensitive sources by only analyzing the code, because both sensitive and insensitive data are obtained through the same APIs. In fact, if we want to do some such code analysis, we confront several challenges. How to systematically discover the input fields from an app's UI, and how to identify which input fields are sensitive, and how to associate the sensitive input fields to the corresponding variables in the apps that store their values. And we can see that the second one is the key problem in our work. To solve these problems, actually we come up with an intuition that a user can simply identify the sensitive user inputs and insensitive user inputs when he uses these mobile apps. Then if we can mimic how a user looks at the UIs, then we can also discover the sensitive input fields. Fortunately, we have some techniques to render the statically defined layouts to the UIs. And currently, the mobile platforms provide some kind of statically defined layout formats for the developers to define the UIs. And the rapid development toolkits can render these layouts to the UIs. The rendered UI is close to what the users see on the smartphone screens. With the rendered UI, we can then associate the text labels to the input fields based on some physical locations or based on some techniques. Here you may want to ask why we do not use the XML file or XML structure directly to associate the text labels to the input fields. Here are some reasons that many developers define the relative positions of the widgets, which are not what users perceive. In this case, XML structure does not guarantee that sibling widgets are physically close, and the relative positions do not intuitively show the correlation on the UI. For example, there are two labels B and C and one input field A, and their positions are defined as B is above of A and C is left of A. Then we cannot directly say that whether B or C is correlated to the input field A. And we also see some real cases in Android apps that they define the UIs by column instead of by row. For example, for this table-like UI, usually we define it by row. Like that means in the XML file, input 1 is close to label 1, and input 2 is close to label 2. But some developers define it like this. They put the two labels together and the two input fields together. And in such cases, if we directly use the XML structure or the XML trees, we cannot tell which input fields are correlated to which text labels. Then, based on the intuition, we propose SUPOR, which is a precise and scalable approach to detecting sensitive user inputs in mobile apps. This is the whole view of SUPOR. SUPOR takes as input a mobile app and outputs the bindings of the sensitive user inputs and the variables in the code to enable some further analysis. And SUPOR itself consists of three parts. The first one is to statically parsing the layouts and rendering the layouts to the UIs. Then SUPOR tries to determine the sensitiveness of the input fields. At the end, it tries to bind the discovered sensitive user inputs to the variables in the code. At the very beginning, we need to know which layout files contain input fields, because we don't want to spend effort on those layout files that do not contain any input fields. And with these initial discoveries, SUPOR can render the layout files to the UIs, and the UIs are close to what the users see on the smartphone screens. They can use some tools like the ADT in Android. For example, if we render layout file A, we can get this. But if we render layout B, we can get this. With the rendered UI, SUPOR can extract this important information for subsequent use. For the marked area, SUPOR can get the text, the hint, and the coordinates of the UI widgets. The text and the hints are what the users see on the smartphone screen, but the coordinates are used to associate the text labels to the input fields. With all the information we've gotten, we can now determine whether an input field can contain sensitive information or not. This is a three-step sensitiveness analysis. At first, we want to see if an attribute of the widget definition can indicate the data is sensitive. This example shows a sensitive input field. But if the sensitiveness cannot be determined by this simple step, we need to show that if the hint of the input field can contain some sensitive keywords. For example, in some apps, the hint can tell the user to enter password. And in our previous examples, the hint tells the user how to enter the data. If the hint contains sensitive keywords, the input field is viewed as sensitive. But if not, we need to analyze the corresponding text label to see if the text label contains sensitive keywords. In our previous examples, the text label comment does not match any sensitive keywords, then it indicates an insensitive input field. But the labels card number and expiration date can indicate sensitive input fields. The first two steps are simple, but here comes a challenge that how to precisely associate the correlated text label to a given input field for the third step. An intuition is that the labels at a different position relative to the input field have different probabilities to be correlated. Here are some examples. The labels can be at the left of, at the right of the input field. It can also be above or below the input field. Then we can assign the position-based weights to the labels at different positions. And the smaller the weight, the closer the correlation. In fact, we divided the UI plane into line parts based on the borders of the input field. The labels at left of the input field and above the input field are most possible to be correlated. But the labels at the bottom corner, right bottom corner, are most impossible to be correlated. Then to show how the text label is associated with the input field, we design a geometry-based correlation score computation. For a given input field and a text label with the known coordinates, we first compute a correlation score for each pixel. This computation takes into account both the distance and the position-based weight. And with this correlation score for each pixel, we can compute an average score for the text label. But usually, an input field may have more than one alternative labels. SUPOR selects the one with the smallest correlation score. One example is that in this example, both fields, card number and expiration date, have 3 alternatives. And their correlation scores are computed here. Based on our policy, the label card number is associated with the number field, and the label expiration date is associated with the date field. Now we have the text for the label text for each input field. We want to determine whether this input field can contain sensitive data. we propose a simple keyword matching approach with a predefined sensitive keyword dataset. In the examples, the label card number and expiration date matches the sensitive keywords. Then those two input fields are sensitive. But the label comment does not match any sensitive keyword. Then the corresponding input field is insensitive. Now I want to show how we build the keyword dataset. We crawled more than 50,000 apps to get all the text in these apps and extract this text into words or phrases via some NLP techniques. And we selected the top frequent words or phrases and manually inspected these words and phrases to get an initial sensitive keyword dataset. Next, we added the synonyms of the selected sensitive keywords to the dataset. Now we finished to build the sensitive keyword dataset. You may want to ask, is it effective or why it is effective by using this simple keyword matching approach? It is effective because recently the smartphone screens are usually small and the phrases or the sentences are usually short. And we find out the most relevant text label and we only alias the text in that label instead of alias many labels. After determining which input fields are sensitive, we want to bind that the discovered sensitive input fields to the variables in the code to enable some further code analysis. And the identifiers are referenced in the code, which helps SUPOR to find out the corresponding variables in the code. But one problem is that different layout files in an app may have input field with the same identifier. For example, in this example, the input 1 for the card number is sensitive, but the input 1 for the search keyword is insensitive. So if we directly associate the identifier to the code directly, then we cannot distinguish the references of sensitive user inputs to the insensitive ones. We solve this problem by leveraging some kind of backward slicing. In this example, we know that input 1 can be either sensitive or insensitive, and we can find out all the references of input 1 in the code. Then, in order to find out which reference is correlated to the sensitive input 1, we find out the backward slices for all the references. For the first reference, the backward slice is something like this, and by further checking this slice, we can confirm that the input 1 here is associated with the widget defined in layout billing information instead of the widget defined in the layout search. Then SUPOR can mark the corresponding variable text input 1 as sensitive. For the second reference, a similar slice can be found like this, and then the widget is actually associated with layout search. Therefore, the corresponding variable in the code is insensitive. Now I want to have a short summary of our design of SUPOR. SUPOR statically passes the layout files and renders the layout files to some UIs. Then SUPOR associates the text labels to the input fields and determines the sensitiveness of the input fields. At the end, SUPOR binds the discovered sensitive input fields to the variables in the code to enable some further code analysis. And based on the design, we built SUPOR on top of some existing tools and only for Android apps. And we limited the type of input fields to a small set of user inputs in Android apps instead of analyzing all possible user inputs in the apps. And we also implemented a sensitive user inputs disclosure detection system to demonstrate the usefulness of SUPOR and evaluated the SUPOR and the system on 16,000 apps. The UI sensitive analysis part, including rendering the layouts for all the layouts in an app, is quite efficient. More than 96% of the apps requires less than 10 seconds for this part. And the average analysis time for one app is only 5.7 seconds. And we manually examined 40 apps of the apps with the input fields and found out nearly 500 input fields. We define true positives, false positives, and false negatives as follows. If a sensitive user input is identified sensitive, it's a true positive. If an insensitive user input is identified sensitive, it's a false positive. If a sensitive user input is identified insensitive, is false negative. And we use recall and precision to describe the accuracy. Both of them are 97.3%. That means we have low false positive rate and false negative rate. And for the 40 apps we examined, actually 149 input fields are identified sensitive. 1/3 of these identified input fields are identified by analyzing the interesting attributes, and 27.5% of them are identified by matching the input hints to the sensitive keyword dataset. And we can see that 38.9% of the input fields are identified by analyzing the corresponding text labels. This indicates the importance of associating the correct labels to the input fields. And we have some false positives and false negatives. One cause for the false positives and false negatives is that SUPOR does not have sufficient context to identify the sensitive keywords. For example, security answer is a predefined sensitive keyword, but in some apps, the UIs only have answer instead of security answer. But answer is equal to security answer within that context. But answer is too general, so SUPOR does not consider answer as a sensitive keyword. Then this may lead to some false negatives. And in some other cases, hate of a human being is sensitive, but hate of an image file or a PDF file is insensitive. But we treat hate as a sensitive keyword, then this may cause some false positives in some cases. In addition to the keyword part, SUPOR sometimes incorrectly associates the text labels to the input fields. That may lead to some false positives. This is an example. In this example, we have one label. This is a long sentence, and two input fields, the email address and the delivery instructions. In fact, this long sentence is a supplemental description of the email field. But when SUPOR tries to determine the sensitiveness of the delivery instruction field, it cannot say that this field is sensitive by only analyzing the hint of this field. Then it will try to find out a label of this field. And unfortunately, it associated this long sentence to the delivery instruction. And this long sentence happens to have the sensitive keyword email. Then SUPOR marks this delivery instruction as a sensitive user input. This is a true positive. This is a false positive. For the sensitive user inputs disclosure analysis part, the whole throughput is about 11 apps per minute on a cluster of 80 servers with 3 apps analyzed on each server in parallel. And we manually examined 104 apps, found that the false positive rate is about 8.7%. In addition to the errors of identifying sensitive user inputs, the limitations of the underlying entity analysis framework is the major cause of the false positives. We do not count the false negatives of this part because we do not have an oracle of the apps, and it's not easy to track the data flows manually in the apps. So we only have the false positive read here. And here are some real cases. In the first one, the weight, the height, and the age are identified as sensitive. And in the second one, the credit card number, the card number, the security number, and the holder's name are identified as sensitive. And these data are discovered to be disclosed to some public channels. These two cases and the two images are rendered by the by SUPOR instead of snipped by at runtime. And we also carefully examined the 44 apps among the 104 apps that send sensitive user inputs via network. We found that only 10 apps adopt HTTPS connections. That means most transmissions in the apps are in plain text via HTTP. We cannot say that these disclosures are malicious, but such behaviors may lead to some privacy leakage of the user's sensitive data. Next, I want to talk about some related work. This UIPIC is also published in Usenix Security 2015, and it also aims at detecting the sensitive user inputs in mobile apps. I want to compare SUPOR and UIPIC from several aspects. For building the sensitive keyword dataset, SUPOR uses the top frequent sensitive keywords and adds some synonyms of the selected keywords. UIPIC discovers the keywords via machine learning technique based on an initial keyword dataset. And the current version of SUPOR only focuses on a small set of the input type, a small set of the user inputs. But UIPIC focuses on more types of user inputs. And when determining if the user inputs are sensitive or not, SUPOR focuses on the interesting attributes and try to match the input hints to the sensitive keyword dataset. In addition to these two areas, these two fields, UIPIC also uses the layout descriptions to see if the corresponding input field are sensitive. For example, some names of the references may contain some sensitive keywords, like the name of the ID might be added password. Then this indicates that the input field is a password field, or this is added email. That indicates that the field is an email field. And we can improve SUPOR by taking into such information into account in the future. If both approaches cannot determine the sensitiveness of the input field by analyzing the attributes, the hints, or the descriptions, we need to associate a text label to the input field. SUPOR tries to find out the most correlated label in the rendered UI, but UIPIC uses the sampling labels in the XML files instead of the physical enclosed or the most correlated. Then this approach may fail in some cases that define the widgets using relative positions, or in some cases that I talked about earlier. Next, at the end, to conclude our work, we started the possibility of detecting sensitive user inputs, which is important but mostly neglected sensitive sources in mobile apps. And based on our intuition, we propose SUPOR, which is among the first known approaches to detect sensitive user inputs, and it has a high recall and precision rate. SUPOR mimics from the user's perspective by statically rendering the layout files to UIs, and it then leverages a geometry-based approach to precisely associate the text labels to input fields. At the end, it utilizes the textual analysis to determine the sensitiveness of the text in the labels. In addition to evaluate SUPOR, we also perform a sensitive user input disclosure analysis. and the false positive rate is about 80.7%. This is to demonstrate the usefulness of SUPOR. And that's all. Thank you. And any questions?
Thank you for the talk. Could you please expand on how you got the weights for the distances that the text label would be from the blank?
Okay. You mean this part? How we get the weight? Actually, at first, we tried a lot of approaches, and at the end, we just manually assign some weights based on our observations. And we tried to evaluate these assignments to a lot of apps to see if these weights works. And actually, they works fine. So we use these weights.
Okay,
Thank you. Any other questions?
Right. So once you identify the sensitive input fields in the whole application or whatever you're testing, what is the next step of how do you use those fields, and like what is the next step of once you identify the sensitive fields in a particular application? What will be the next step?
When we identify the sensitive user inputs in the apps, what is the next step?
Yeah.
The next step is we try to bind the sensitive input fields to the variables in the code. We know that these input fields are sensitive, but we need to know the locations of the references in the code to enable some disclosure analysis or some vulnerability analysis. So the next step is binding the variables to the code. Is this clear?
Yeah, I saw this part of it, but I'm wondering what once you bind it to the particular text field, that which input field is it referring to? What do you do after that? Like once you identify that field, then you can just trust it on any application and get the results.
I don't quite understand your question. Can you repeat it?
So you can
Could you use your microphone out there, please? No, the person in there.
Am I audible now?
You can let you come up.
It's not. So my question is, once you've identified the input fields which are sensitive, then you bind it to the text fields which according to one of the three approaches that you discussed. Once you do that, then the whole finding you can directly deploy it as it is on an app, or do you need to use some other findings on it to make it something that you can deploy directly on an app?
Well, you see that after we identify the sensitive user inputs and bind these input fields to the variable in the code, then this is the end of SUPOR. But we can leverage such information to do some code analysis. Because we know that which variables are sensitive, then we can track the data flows of these sensitive variables.
Okay.
Is it clear?
Yeah.
Does this application provide any security to the app, mobile apps, or is it just the analysis of what is sensitive and what is insensitive?
It is just an analysis of what is sensitive or insensitive, and we also perform a further analysis to see whether these sensitive data are disclosed to some public channels. It is a static approach. It's just a static program analysis. If we extend this approach to a dynamic program analysis, we can try to alert the user that to tell the users some sensitive data are disclosed to some public channels, and the users can let it go or just stop it. Okay. Is it clear?
Yes.
Thank you. Any other questions?
What format do you need to take the applications in order for them to be analyzed by SUPOR?
What format of the applications we can use in SUPOR, right?
So how do you need the applications? Can you just pull them down from the store? Do you need the source code or the APK in the case of Android?
Currently, we directly analyze the APK file of the Android apps. Do you know the APK files? So is this answered your question? Okay.
Didn't do anything.
Yes, it's
Okay. Does this work at the client side or the server side?
Client side.
Client side.
Yeah.
So are you going to extend it to the server side? Because it seems like it would be a better idea to analyze applications from that side.
I beg your pardon. What do you mean by client side or server side? Because
I mean-
this is a standalone tool, so you can apply it to everywhere.
You can apply it everywhere.
Yeah, sure.
So, for example, if I want to analyze a website that I'm using for how secure and how much of my data it's sharing, or how secure my data is on that website, this can work?
We can extend it to the server side that you can upload one APK file to as the input of this tool, and then it will tell you the results of the disclosures or the sensitiveness. And you can apply it to the app market stores to analyze a lot of apps and tell which apps have some bad disclosures, and then we can notify the developers of these problems. Or as a developer, you can use this tool to analyze your own apps and see if there are some disclosure or bad disclosure paths, then you can improve your own apps.
Okay.
Is it clear? Yes. Thank you. So any other questions?
Have you disclosed information you find on the apps that are sending information to public channels? We have a database of information on the apps sending, on plain HTTP.
You mean, do we find some information, some
On the apps.
on the app?
That you find that are actually sending sensitive information to public channels.
To public channels like HTTP?
Yeah, I mean, you said you had 60,000 apps.
Mm-hmm.
How many? You said that many of them sending sensitive information through public channels, right?
Yeah.
Do you have the information on those apps that are, let's say, vulnerable to this information, to these information leak?
We do not find if these disclosures are really leakage. We just say that if there are some sensitive information are sent to some public channels, but we do not say if these are bad or good, because for some apps, the user ID or password are sent through HTTP to the servers for verification. All such cases are viewed as a disclosure. We do not say that if these are bad or good, or if they are intended.
Okay.
May I answer your question?
Yeah, I'm just saying you have published that information, that you have the results you have.
Do you publish the information? No. So, any other questions? So if you don't have any other questions, then we can end this seminar earlier. And thank you for attending this seminar.